Calculus is mainly about three things: limits, derivatives, and integrals. We have finished with limits and derivatives. So now we're headed toward integrals. And we're going to take what seems like a completely different turn. We're going to look at a completely different kind of problem that we're looking at that really by all means should not have anything to do with what we've been studying so far. But it turns out it has everything to do with what we've been studying so far. So what we've been studying so far is getting the rate of change, how fast something is changing at a specific instant. So getting a slope with 1 point instead of 2 points. That's what we've been working on. That's what everything's been about. The rate of change of things, the instantaneous rate of change of things. Now we're going to do something that looks completely different. And it all starts with this. So this is an exploration, an in-class exploration. So usually I do this in class, and it is about velocity, acceleration, area, and some things like that. So the first thing I want you to do is download this paper, which is posted in the Google Classroom. It's probably at the end of all the videos, but you need to do that first. So what I want you to do is, this is designed for you to answer completely on your own without any foreknowledge at all. So go ahead and download this and answer everything to the best of your ability, and then come back and we'll discuss it. All right, I'm assuming you have now done all of this and you're back to discuss it. So we've got a hummingbird, and it's traveling in a straight line. I never said it was a straight line, so we'll say now it's a straight line. At a constant rate, 4 meters per second for a period of 2 seconds. So we're starting with things that you trivially already know. And one of the things we do with mathematics is, if I want to understand a situation that I don't know, I will start by looking very carefully at the things that I already know. And if I look very carefully at the things that I already know, I can often pull out an idea that helps me to approach the thing I don't know. And of course, the number 4 is the one that you don't know how to do. But number 1, everybody knows how to do. Number 2, if you didn't know how to do it, just read it. It tells you how to do it. And number 4 is the one we're headed for. Okay, so we're starting with this really very trivial example where the hummingbird is going at a constant rate. R equals 4 meters per second for a period of time t equals 2 seconds, from t equals 0 to t equals 2. And I could have written a closed interval, but I didn't. All right. So, okay. So, A, what distance does the hummingbird travel? So this is number 1. I should probably label this in class exploration. Could have done this ahead of time, but I didn't, did I? No sense crying over that spilled milk. Distance, velocity, and area. Okay, here's number 1 of that sheet. Okay, so we have this, and so we go back to 5th grade and say, okay, distance is rate times time. So that is, and let's be good physics students and throw in the units, because the units are going to reveal some interesting things as we go along. Times 2 seconds, the seconds cancel, and we have meters, so it's 8 meters. Okay, whoop-de-doo. All right, part B. Now, here's the part where we take this thing we already knew and we start looking at it a little more deeply. So in part B, we're going to look at a graph of that velocity function. What did your graph of the velocity function look like? I hope that because it says you are traveling at a constant rate of 4. So remember, a lot of people, the mistake that people often make is graphing this like this. All right, that here's a constant rate of 4 and the slope is 4, right? That is not what this looks like, okay? Because this is not a graph of position, it's a graph of velocity. It says, sketch a graph of the velocity function, okay? So this is not position here, it's velocity, and it's measured in meters per second, all right? And this down here, this is your time axis, so it's measured in seconds, all right? So here's t equals 4, and here's, that's v equals 4, here's t equals 2, and a constant velocity of 4 looks like this. So that's v of t equals 4. All right, and then, so that's a graph of the velocity function. That's part B. All right, sketch a graph velocity function. We did that. Okay, now the area bounded below by the x-axis, above by the velocity curve, on the left by the vertical line t equals 0, and on the right vertical line t equals 2 is called the area under the velocity curve. From t equals 0 to t equals 2, what is the area of this region? All right, so here's our vertical line t equals 2. And then we have the x-axis, the y-axis. So we're going to start talking a lot about the area under a curve. And what we mean by the phrase the area under a curve, right? The area under the curve. It could be velocity, it could be something else. Spoiler alert, could be something else. All right, the area under the curve for over a certain time means look at vertical lines defining the beginning and ending of an interval and find the area between the curve and the x-axis. That's what we mean by the area under the curve. Of course, if the curve is negative, then the area might, technically speaking, be over the curve, but we still call it the area under the curve because we don't want to necessarily have to specify. All right, so then it says, what is that area? What is the area of the region? Well, area equals, well, it's 4 times 2, which is 8, all right? But consider that the velocity is in meters per second, so this is still 4 meters per second times time is, this axis is in seconds. So we can include the units and still end up with 8 meters, all right? So the first thing to notice is that by finding the area under this velocity curve, you come up with, and you probably noticed this is the answer to question number 3, that the distance traveled and the area under the velocity curve are the same. Distance traveled and the area under the velocity curve are the same. All right, so that's going to be one thing that's going to carry us through a lot of things. Now, I said distance traveled here. Technically, what is the same as the area under the velocity curve is called displacement. I'm consciously working with all positive velocities so that I don't have to worry about the difference between distance and displacement, which we'll talk about later. Okay, now, I wonder if this equality will continue to hold.